Yo, 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 it's your boy. Just kidding, guys. This is Mr. Snyder. Today's video is going to focus on single displacement reactions, or what we might have formerly called them, single displacement reactions. Single displacement reactions are a type of oxidation reduction reaction. Normally we just call these redox reactions. You'd be familiar with these in the context of galvanic cells from the very last unit of sophomore chemistry. Bottom line, redox reactions are considered to be electron transfer reactions. And normally we have kind of like half reactions, right? And we'll get to this at the end of this unit. But when we talk about an oxidation, say half reaction, this is the portion where we are seeing a loss of electrons. You probably remember the mnemonic LEO. This is in contrast to the reduction half reaction, which implies a gaining of electrons. We've, again, kind of talked about this as like the GER part of the reaction. So the implication here is that the oxidation number, or the state, the oxidation state, must change for two different elements as electrons are transferred. And it's interesting that we're just really talking about this now because many types of reactions are actually redox reactions. So we've already talked about synthesis and decomposition. We'll also, towards the latter part of our unit, talk about combustion reactions. All right, so let's get to it. In a displacement type reaction, an ion or an atom within a compound is replaced by an ion or atom of another element, okay? In order to determine whether a reaction will or will not take place, we have to use the activity series. The activity series we're going to use this year is a little bit different than maybe what we've seen before, where not only do we have kind of this rank order list of metals, we also have kind of a discussion concerning oxygen as to whether metals will react with, say, water or perhaps acid, and we'll get into this here in a moment. So the first type of displacement reaction we are going to discuss is that of metal displacement. When we talk about metal displacement, we're going to say that a metal in a compound can be displaced by another metal in the elemental state. And again, the way that this works is that metals listed in the activity series have the capacity to react with any metal that is contained within a compound that is below it. Okay, so let's get into some examples. So let's say that I am dealing with solid magnesium, and I want to determine, is it going to react with our cupric nitrate? Well, I would confer with the activity series, and I would identify that magnesium is here, whereas our copper is down here. This implies that magnesium has the capacity to displace copper. So essentially, we're just going to exchange these two metals. When we do so, we have magnesium nitrate that's going to form. We know that it is in a 1:2 ratio, given that our magnesium carries a charge of 2+, nitrate is 1-, so we have a properly balanced ionic compound there. That will be in the aqueous state, implying that it is soluble in water. And again, we have our displaced solid copper, okay? Again, the reason this happens is because magnesium is higher on the activity series than copper, okay? All right, let's take a look at another example. Let's say we want to determine whether silver has the ability to displace nickel from nickel nitrate. So again, I take a look at my activity series. I identify where silver is. Silver is really down, kind of far on the activity series, where this whole group of atoms here is actually deemed mostly unreactive. We're trying to determine, will it displace nickel? And in fact, because it is lower, it does not have the capacity to. So we'd merely put an X here, and we'd indicate that no reaction is going to take place, okay? And what we just discussed really should be familiar from sophomore level chemistry. All right, the next type of displacement reaction we're going to discuss is that of halogen displacement, okay? Or maybe just kind of generically non-metal type displacement, but we largely focus on the halogens. So halogens within a compound can be displaced by another halogen within its kind of normal standard diatomic state. As we progress down the periodic table, so as we move down group 7A, the halogens aren't as easily reduced. All that really means is that they become less reactive. So Fluorine has the capacity to displace any of the other halogens, chlorine, bromine, and iodine. Bromine, merely just iodine. Iodine does not have the ability to displace any other halogen that is contained within a compound. So let's take a look at our first example here. We are going to react gaseous molecular chlorine with potassium bromide. We're going to see, can this actually take place? So at the bottom of the activity series that y'all are going to receive on Monday, we actually have a little section here just kind of reminding you of that order of reactivity. Given that chlorine is in fact higher on this activity series than bromine, we find that it does have the ability to displace it. So chlorine, and bromine will kind of swap spots there. Okay. As that happens, we are going to form potassium chloride, again, which is super soluble in water. So we write aqueous. And then again, we've displaced our bromine, so Br2. Bromine, because its electron cloud is really, really large, though it is nonpolar and merely has London dispersion forces, the polarizability of the bromine molecule is really, really large. And as a result, those dispersion forces kind of manifest into this really, really large dipole. And we actually find that it is a liquid at room temperature. So if we're examining this equation, everything looks pretty good except for the fact that we don't have conservation of atoms or conservation of mass, and this requires that we go through and we balance this guy. So we merely stick a 2 in front of the potassium bromide, stick a 2 in front of potassium chloride, and it would appear as though we are in business. Just a reminder, we know that this is the formula for potassium chloride because of the charges that these elements take on. Okay, nice 1-to-1 ratio there. If I take a look at another example, let's say between iodine and sodium bromide, again, referring back to the bottom part of the activity series, we find that because iodine is lower than bromine on the activity series, this reaction will not occur. So again, we merely write no reaction, maybe stick an X through our reaction arrow there. Pushing on, we are going to take a look at the last type of displacement we're going to discuss, that of hydrogen displacement. Okay. We're going to say that all alkaline metals and some of the more reactive alkaline earth metals have the ability to displace hydrogen from cold water. So when something like sodium comes into contact with water, a reaction will take place. And it's really formulaic. It's essentially what we've just seen, in kind of that first example where a metal is kind of just replacing another metal. I would get in the habit of rewriting water as HOH because it is literally the sodium that's going to be displacing that hydrogen right there. Okay. As this happens, we are going to get NaOH that forms. Nice 1-to-1 ratio, again, giving the charges of the sodium ion, that sodium cation, in addition to the hydroxide polyatomic there. Again, super soluble in water, so it gets the AQ designation. And as we've displaced hydrogen, hydrogen again is part of that Hunkelbrief diatomic series, which is to say that it will be H2, which is a gas. Hydrogen's a gas, really low molecular mass there, very few electrons. So nonpolar, not really polarizable at all, really, really, really weak London dispersion forces. So everything looks good right now, again, except for the fact that I haven't balanced it, right? Apparently, I know some hydrogens have got kind of out of whack. So in order to balance this, it looks as though I'm going to merely add a 2 here, 2 here, and a 2 here. And now I have 2 sodiums, 4 hydrogens on both sides, and also 2 oxygens on both sides. Okay. Another example, we find that though it is less reactive, calcium still has the ability to displace a hydrogen from our water molecule. So again, calcium and that hydrogen will swap spots. I'm going to end up getting calcium hydroxide, again, in the aqueous state, displacing the molecular gaseous hydrogen. A couple things immediately kind of jump out at me. I know that calcium carries a charge of 2+, hydroxide's 1-. So as written, this is an improperly kind of balanced ionic product here. I have to attend to the fact that I need 2 hydroxides. From here, now it would look, again, that mass has not been conserved. To balance the equation, I use a coefficient of 2 to make sure I've not lost any hydrogens, oxygens. Cool. In kind of a separate portion of hydrogen displacement, if we refer back to our activity series again that you will get on Monday, some metals are super reactive and so have this ability to react with cold water and acids. As we progress down the activity series, we lose this ability to be as reactive, and so metals will still have the ability to react with gaseous water, right? Steam, but normally not just like room temp or cold water. So as we kind of move down kind of this middle section, steam, sure, but also acid, right? So that's the other type of hydrogen displacement reaction we're going to take a look at, is that many metals, even ones that don't necessarily react with water or even steam when we get down here, do have the capacity to displace a hydrogen as it reacts with an acid. So just to kind of restate that, many metals, including those that do not react with cold water, are capable of displacing hydrogen from steam or acids. Nickel, tin, lead, those are really limited in reactivity and only have the ability to react with acid, not even steam. Okay, so let's take a quick look. As the zinc and the hydrogen look to kind of swap spots there, I'm going to form zinc chloride. Again, soluble in water. We will get into solubility rules over the coming days. Displaces the hydrogen gas. Zinc is one of the metals I've asked you to commit to memory in terms of its charge, which is 2+, which is to say, again, I need to look to balance this. It looks as though I've seemingly created chlorine atoms out of thin air. Dropping a 2 there just to make sure the chlorines are balanced, in addition to the hydrogens, okay? Kind of another example, magnesium, though it is, actually magnesium is more reactive than zinc. We can work this as kind of a follow-up example. Again, magnesium will displace the hydrogen, creating magnesium chloride, 2+, 1-. Again, the need to stick in a 2 subscript there to make sure that ionic is neutral in charge. Magnesium chloride is aqueous, which is, again, to say that it dissolves in water. And then we kind of form our hydrogen gas there as well. Just make sure everything is right. Dropping a 2 coefficient just to make sure we've conserved for atoms and therefore mass. Okay. All right, in kind of a separate last section of this video, we are going to examine the difference between molecular equations, ionic equations, and net ionic equations. Okay. So, the very first thing I want to discuss is molecular equations. This is what we have been most familiar with previously in chemistry. So this is where the formulas of all the compounds are written as though every single species, right, so every single reactant or product exists as molecules or whole units. And this may not be really conceptually accurate. What does a better job attending to reality are ionic equations, where we can take something that is aqueous and given the ion dipole intermolecular attractive force that's going to exist between ions and the solvent water, we can actually show them as free hydrated ions. Okay, again, getting towards reality a little bit better. And then ultimately in our net ionic equations, what we do is we remove what we call spectator ions. Things that really don't participate in the reactions, and this allows us to key in on really just the major players. And that also allows us to kind of isolate that electron transfer process that I was describing earlier, and we can more easily kind of track, what is being oxidized, what is being reduced. It really just kind of shows us, like I say, the major species. Okay, so let's take a look at kind of all of this in play. The sequence of steps we're going to follow is to always come up with the molecular equation first, then the ionic, and then progress down to the net ionic. So in the following example, I'm going to take solid aluminum and react it with our plumbous nitrate. As this happens, we could verify on the activity series that aluminum has the capacity to displace lead. As it does so, it's going to form aluminum nitrate. I look up the charges, 3+, 1 minus, I know that I need to have 3 equivalents of the nitrate in order to properly balance that product. Aluminum nitrate is soluble in water. I will indicate that with the AQ. Again, I've displaced now just lead in kind of its standard state, just PB. That will be solid. In order to balance this equation, I drop in a 2, 3, 2, and a 3. Okay. Again, that first step towards kind of product prediction, we had to verify that aluminum is higher than lead on the activity series. Aluminum, and then lead is down here. So they simply kind of swap partners. At that point, we just make sure we've rebalanced our ionic products. Okay, we've also indicated the state of matter. So this whole thing right here constitutes our molecular equation. But again, going back to one of our last units on intermolecular attractive forces, we know that water, given its very strong dipole, has the ability to break down ionic compounds as ion dipole intermolecular attractive forces start to kind of take hold. So what I'm going to do is I'm going to show all aqueous species as these kind of free hydrated ions. So I still have my 2 equivalents of my solid aluminum. I have 3 equivalents of my Pb2+ that has been solubilized. Okay, so I've separated that out from the nitrate. I also have 6 equivalents of the NO3 1-, again in the aqueous state. That 6 is coming from the fact that within this kind of balanced equation, with every unit I have 2, but I have 3 equivalents, so 6 in total. I have my 2 equivalents of the aluminum 3+ aqueous on the product side, plus 6 equivalents again of the nitrate 1-, and then 3 equivalents of the solid lead. Okay. So this, as written, represents my ionic equation. And this is a little bit more indicative of what is actually taking place. The idea is that you have solid lead initially, maybe sitting inside of some beaker, and then freely floating around in solution is going to be my 2+ and my NO3 1-. Like these have been dissociated. They're no longer kind of together as maybe this formula would imply. They are just interacting with the polar water molecule, okay? Again, on the product side, as the reaction kind of takes place, you have these ions freely floating around in solution, whereas now we've formed our solid lead. So in a final step, to generate the net ionic equation, I remove what's called a spectator ion, and that means that it doesn't directly participate in the reaction. And that's going to be anything that we see on the left side of the equation and the right side of our equation that is not changed, right? And the only thing that hasn't really changed is going to be our nitrate. So we have 6 equivalents of the nitrate on the left side, 6 equivalents on the right side. Maybe just label this as our spectator ion for good measure. Okay, and it may be possible that we have more than one spectator ion, but in the case of this single displacement type reaction we're evaluating, we're just going to have one. So now we just rewrite our net ionic equation, having removed that spectator ion. So we have 2 Al solid plus our 3 equivalents of our Pb2+, again aqueous, and that is yielding 2 equivalents of the Al3+ and aqueous plus 3 Pbs. So this right here is what we call that net ionic equation, which really just kind of focuses again on those major players. Just as a reminder, to start this video, I told you that these single displacement type reactions are a type of redox or oxidation reduction reactions. Going back to oxidation kind of state or oxidation number rules from the other day, we know that an element in its standard state has an oxidation number of 0. If you're an ion, then you are going to have the oxidation number equivalent to the charge of that ion. So we kind of label all these. And what we find is, as part of this electron transfer process, as aluminum goes from an oxidation state of 0 to +3, this means that we have a loss of electrons. So lost electrons. This means that this has been reduced. If we take a look at the lead ion here, it goes from an oxidation state of +2 over to 0. This implies that we have gained electrons. And as a result of having gained electrons, we know that this has been oxidized. Awesome. Hey, thanks, guys.